In progress. Wait.
Assalamualaikum, good morning. Can you hear me?
Yes, Doctor.
Yes, good.
Thank you very much. Right. So let me share you. Can you see my slide?
Yes, sir.
Right. So we begin with chapter 0 on the revisit of the theory of control system. Okay. So I will talk about the introductions, control system types, open loop control system, closed loop control system, important definitions, objectives of control system, and some design steps. So in order to understand this particular subject, you must have a good understanding on the modeling and control, which is last semester. Okay. Minimum pass. Okay. So as you know that control systems is everywhere in our lives. Okay, it's very vital, important. Okay. For examples in aircon system, for examples in the vehicle, okay, and many system, transportation and so on, okay. Basically on the man-made control system, okay, washing machines, antenna for radio, okay, or for the satellite, okay, for astro dish and so on, okay, for the military rocket and missiles, and particularly on the robots in the manufacturing system, manufacturing factory, okay. So for human, okay, is also we have a control system, okay, which is on the sensor is on the human eyes, where you can control and maneuver, okay, and carrying things using hand. And also our body have chemicals that is what you call as a hormone, okay. For example, hormone for the to detect the blood pressure, the level of sugars in our body, all are using chemicals, okay, which is also need to be controlled on top of the physical body of the human, okay. So basically, control system, when we talk, we must have input, That is a must. Okay. Input, which is will stimulate the system, okay, inside the control system towards the desired response, toward the desired set. And output response, which is the actual, the real behavior of the system, okay, which will be the output, okay. So, for example, in the elevator system, which is in many buildings, okay, particularly in the our faculty, okay, we have 5 input elevator, level 1, 2, 3, 4, and 5. Okay, so we press the level that we mentioned the input, and the output is the output of the elevator that will bring you to the required level that you want. And this is what we call a control variable. So the types of control system, it can be positions control. Okay, for example, robotic systems, crane systems, elevator, satellite tracking, and so on, or speed control. For example, for a car, okay, aeroplane, washing machine, okay, climbing robots, and so on. For example, in washing machine, you have slow rotations when it wash, okay, and then high rotation when it spin, okay, to remove the water from the clothes, okay. And temperature control as well, where we control the temperature that we want, okay. Let's say for a building, for a class is 23 degrees of Celsius. So the cold air will blow until the temperature of the room, 23 Celsius, okay. And then for industrial control, for example, in pharmaceutical industry, food industry, many process industry, all are monitored and controlled in real time, okay, in the control room. So basically, we have the open loop and closed loop control system, where open loop is without feedback path. Okay, is input, go to the controller, go to the process, and then output. And for this particular system, a lot of disturbance from outside will enter to the system that create the noise, okay, unnecessary signals, right? So the input or references is the signals that we want and the output. But when the disturbance 1 and disturbance 2 enter to the system, it will mix with the input to create an output. So meaning that your output have 2 signals, okay? The real output plus disturbance. So this disturbance must be removed, okay, as soon as possible. What is the example of disturbance 1 and disturbance 2 is, first is from the 3-pin plug of the wall, which will give you a 50 Hertz sine wave. Okay, so that will enter to the system. There you can see that the output signal similar like sine wave oscillations. That is because of the disturbance from the 3-pin plug at the wall. And it also can be come from the handphones, okay? The microwave signals from the handphone also can enter to the system. So that's why when you conduct measurements of a control system, so you must make sure that all these disturbance must be removed, okay? And then closed loop system is where the output signals is feed back to the influence, okay? Feedback meaning like this, okay? There you go, the red color, and goes to the input, okay? So you can see that the blue, the red, sorry, the circles, which consists of the cross inside the circles, we call it as a comparator, okay? Is a comparator. So comparator in reality is from the summing amplifier, okay, from the operational amplifier that is configured as a summing amplifier. So it will become summing junction. We call it as a summing junction, where we have three here, one here and one here, right? So at the feedback path of the closed loop system, there must be a transducer or the sensor. Okay, so this must be hardware. There is no software that replace the transducer or sensor. It must come from the hardware, which will detect the physical signal and convert it to the electrical signal, which consists of voltage and current. Okay, so physical signal, example of physical signals, so for example, is the heat. Okay, the degree Celsius temperature is a physical signal. What else? Let's say 5 bar. Okay, 5 bar is a pressure unit for pressure. Pressure is known as physical signals. Level, for example, 10 centimeter. So that level 10 centimeter is known as physical signals. Okay, all signals that is not electrical base, either voltage or current, is known as a physical signal. That's why some definition need to be understand. That's why we go for revisit here. Okay, for example, modeling, right? So modeling is the subject that you learned last semester, where we model the system based on the transfer function and state space. Okay, right? So it represents the control system in mathematical equations. Okay, even human also have their own mathematical equation, which is different from one person to another person. Mathematical equations of boys and girls also different in terms of their emotion, physical signals. Okay, and emotion and then from the brain signals from the boys and the girls. It's not the same. Okay, the mathematical equations. And then these transfer functions, actually base is a ratio of the output versus input, output over input with the zero initial conditions. And the state space is the, which have a state equation, x dot ax plus bu. And the output equation y equal to cx plus du. Okay. So this is known as the state space representation. So we have two types of model here, transfer function and state space. Both can be used. Okay, it depends on the way you want to model it. And then the block diagram, okay, which consists of block. Each block represent the system transfer function input and output. Open loop and closed loop, as I mentioned before. Okay, and then we have a poles and zero. So poles, the symbol of poles is X, and zeros is circle. Okay, which is located on the S-plane. Okay, which is the real axis and the imaginary axis. Okay, so the poles can be over here, the zeros can be over here. Okay, but once one poles on the right hand side, on the right half plane, so the system is unstable. So this one we call right half plane on the right, and this one is the left half plane. Okay, so all poles must located on the left half plane to make the system stable. Okay, so please remember this axis is imaginary axis, and this one is the real axis. Okay, can you follow me? Guys, don't sleep.
Yes.
Yes,
Right.
Doctor.
And then we go to the next one, which is the output of the system, where a time response. Okay, time response of the system is defined as the output of the system when you inject input, which is the function of time. Okay, so when you give an input to the system, okay, let's say square wave. So this is time domain. And this is the amplitude of the signals. Okay, and then there is the output. Okay, this is the output. Try to follow the input. Okay, so we have two graphs here, two signals in one graph. The square one is the input, and the sign here is the output. And then can be represented in S plane, as I told you before. S plane is a complex plane in a Laplace transform where you have a real axis which is represented by sigma and imaginary axis which represented by j omega. Okay, is a complex number that can be mapped to the graph using a linear graph. So in our subjects, we all learn the time domain and the frequency domain. Okay, so of course, frequency domain, we are using not using a linear graph, but we are using a Bode plot. Okay, to represent the frequency response, the output. Okay, which will be discussed in the future chapter in the subject. And then we have a gain margin and phase margin, which obtained from the frequency response Bode plot. Okay, and then we have a gain crossover frequency and phase crossover frequency. These five, gain margin, phase margin, gain crossover frequency, phase crossover frequency, and stability is the 5 important component in open loop Bode plot response. Okay, frequency response. So we will use this in chapter 3, okay, chapter 3 and 4 in the design of compensator using a frequency response, which will be lectured in chapter 3 and chapter 4. So from the time response and from the frequency response, our objective is the same. We want to make the system stable with a fast response, okay? Because control system is dynamic, okay? It depends on the input that you injected to the system, okay? And we want to see that the output response settle as soon as possible, and then must be less steady state error plus stable. Okay, so that's why we observe the transient response, okay, to see whether the system have a steady state error or not. Okay, steady state error is the error during the steady state phase of the response. Stability. We cannot compromise with unstable system because unstable system is very dangerous to the human life and towards the whole system. Okay. For example, if you go by aeroplane flight, okay. So if the system is unstable, it will crash down. Okay. The aircraft will crash down or suddenly vanish from the radar. MH370, okay? That is a mystery, okay? Unstable system. So we must make sure that the system is stable for human life, safety, and then the system have a very small steady state error, okay? The good one is 0. The difference between the steady state error is defined as the difference between the input and output at steady state. Okay, the good steady state error is 0. But if you cannot achieve 0, something that 0.1 or 0.01 is already good enough. Can be accepted. Okay, so for system with the to describe the stability of the system, we look at the elevator. Okay, so elevator is based on the transient response. If the elevator is too slow, so the passenger will complain and impatience. Okay, if the elevator is too fast or very fast, so we will feel uncomfortable, and will cause vomiting. And if the transient response of the elevator is oscillate more than 1 second, so it will become uncomfortable. That's why stability of the elevator must be as good as possible, plus a good steady state response. Okay. Here is the example, time response. This is a sample of a time response. You can see that this axis is the amplitude, which is represented by the floor of the building, and this is the time. Okay, in second, you can see 3 response here. One is green response, the other one is the yellow response, and the black response. Okay, that is the output. Sample of output: black, yellow, and green. And the blue one here is the input. Input is what level? Level 6. Okay. So when we press level 6, so we can see 3 different output response from the elevator. One is oscillate. This one is slow. And the yellow one is the acceptable. Okay, not too slow, not too fast, but acceptable with 0 steady state error. You can see that for the green response, you have a gap here. So this gap is known as ESS, steady state error. Everybody follow me. ESS, steady state error. Hello? Everybody follow me. ESS, steady state error.
Yes.
I can't hear you.
Yeah.
Okay. So design step. Okay, design steps. Okay, is shown here. If you want to design a system, first you must draw the functional block diagram and schematic diagram. Okay, and then start to model the system. So you must obtain the transfer function. And then you analyze the time and frequency domain using root locus and board plot. Root locus is the tool for design, to design in time domain, while board plot is the tools in design for frequency domain. Okay, and then after that, design the controller. So PID or state feedback or robust or intelligent control system. So in our subject, we focus on transfer function and PID controller. Okay, the rest is other controller will be learned in the elective subject. Okay, that is a revisit introduction. Any question? Any question? Any question, guys?
No for now.
No question. Okay, if no question, Iqbal Ihsan, brother Iqbal.
Yes, Doctor.
I have one question for you.
Okay, Doctor.
What is the hardware that will be used in control system to represent summing junction?
Uh,
Okay. Cannot answer.
I
Brian,
think cooperator.
comparator. Using what hardware?
Cooperator.
Component. Using operational
I'm not sure
amplifier.
that.
Using operational amplifier.
Amplify. Yes.
Brian.
Yes,
Warata.
doctor. There are two Brians.
Oh, tu Brian eh. Brian Chong Ting Tong.
Yes, doctor.
Brian. I have one question for you since you have no questions. My question is, hello?
Yes.
What is S-plane?
Sorry, explain.
S-plane.
Explain. It's a Laplace transform. It's for the Laplace transform to find the poles and the zeros.
To map, not
The
to
to find the position of zeros
map.
and poles.
To mapping.
Yeah.
Mapping, eh?
Yeah.
The tools for mapping location of poles and
Poles
zeros.
and zeros.
Mariam?
Thank you, doctor.
Mariam, are you there? Mariam? Can't hear you. Mariam?
Yes.
Can you give an example of controller in control system? Name of controller in control system. Can you answer?
I'm sorry, doctor. I can't.
Answer. Okay, we go to Izdul.
Yes, doctor.
Name of controller in control system. Example.
PID controller.
PID controller. Very good. Sanzida. Sanzida. Sanzida Rahman. Are you there? Can't hear you.
Yes, doctor.
Okay. What is the give example of input signal of a control system? Example of input signal of a control system. Sanzida,
Yes, doctor. Would you please repeat the question, please?
give me an example of input signal of a control system. Square wave. Okay. Can you repeat?
Impulse.
Square wave, impulse
impulse.
response,
Yeah.
sine wave. Okay, all are can be considered as a control system. Okay, let's go to chapter 1. Can you see chapter 1? Can you see chapter 1?
Yes.
Right, control chapter 1 is about the root locus method. So in chapter 1, we will look at the introduction, the concept, the procedure, how to draw root locus, to construct it, and to adjust the gain of the control system. And then, of course, we have to using a software to assist our design and our construction of a root locus using MATLAB. Okay, using MATLAB. So what is MATLAB? Actually, another Brian, can you answer me? Brian? Second Brian.
Yes, doctor. I can
What
hear.
is the definition of MATLAB? MATLAB is the acronym.
MATLAB is a software used to simulate.
No, what is the acronym? M stands for what? E stands for what? T stands for what? LAB stands for what?
I'm not sure about that.
You're not sure, huh? You're not sure? Okay. Vicky Woon. Vicky Woon.
Yes, doctor.
What is MATLAB, ma?
I think it's a matrix laboratory.
Matrix laboratory, absolutely correct. Okay, is a matrices laboratory. Okay, so please take note. Okay. Right, so as the introductions, okay. What is root locus? So root locus is a method of analysis and design for stability and transfer response of a control system. So when we have the mathematical model, the transfer function, the output over input, then you have a polynomial of the numerator, the top one, which represent the zeros, and the polynomial of the denominator, the bottom one, which represent the zeros. So from this value, poles and zeros, we map to the S-plane, which is imaginary axis versus real axis. Okay, so that's why you get a root locus drawing from there. Okay, so for example, like this. Okay, real axis, imaginary axis. Then you have 3 poles. For example, 3 poles only. So the root locus will be here, example, okay. I will teach you how to draw later on during face-to-face. Okay, this is example. Okay, and then this one. So this one will end at infinity. This one will end at infinity. And this one will end at infinity. So the blue color is the root locus. Okay, the blue color is the root locus. So RL is a graphical representation of the closed loop poles as the system parameter is varied. So along the root locus path, okay, it consists of a closed loop poles. And these closed loop poles have different gain value from one to another along the root locus path. Okay, so thus the root locus gives the transient response spec specifications. For example, OS. OS is not operating system. OS is the overshoot. Okay, overshoots. TP, peak time. T is time, P is peak. So the short form is TP, peak time. TS is settling time. ESS, E stands for error, SS stands for steady state. Okay, and then the stability of the system to make sure that the system parameter is valid. So the concept of the concept is off the mic, please. Aznil, masuk ya. Okay, poles are important in control system as they determine the time response specifications and stability. So open loop poles are easily found. They do not change with changes in the system gain. while closed loop poles are difficult to find, especially for higher order system. Okay. So there is the examples of the difference between the open loop poles and closed loop poles. Okay. Open loop poles you can take from the system transfer function and then map straight away to explain, while closed loop poles are challenging because it is located along the rule of compass, okay, with the different gain values. So closed loop poles change with changes in the system gain. Once the gain change, the closed loop poles value will change as well. For example, here you have a control system which is closed loop. Okay, this is a closed loop. Okay, C over R. Okay, C over R, which is equal to here KGS over 1 plus KGS HS. What is KGS? KGS is the forward transfer function. Okay. What is HS? HS is the feedback transfer function. What is this? This is the summing junction. What is summing junction? Summing junction is a summing amplifier from the operational amplifier, and there is the input and there is the output. Okay, and there is a one wire here connected at the feedback, and then you can see that these signals, we call it as actuating signals, EA. Actually is the error, which is represented by the difference between the input and output. Okay, so as I told you before, the difference between input and output is the steady state error, and we call it as the actuating signals, EA, that give the information to the controller and the system transfer function. Right, so the rule locus concept is basically is a mathematics. Okay, with the system, we consider a system as GS, okay, which is N over D, the open loop transfer function, and the feedback is HS, okay. So the closed loop transfer function is the 1 over 1 plus G multiplied by H, which will produce give this type of equations, the closed loop. Okay, so this one is given, this one is given, okay, and this one you have to derive the closed loop transfer function. So zeros of the transfer function is stand for the zeros of GS and poles of HS, while poles of TS is not immediately known and it affected by K. K is the gain. Okay, once the gain value is given, so it have the closed loop poles value. Okay, for example, if we have a open loop transfer function, which is here, GS equal to S plus 1 over S plus 2. Okay, let me write for you. G S plus 1 S plus 2. So what is the zeros open loop? Zeros open loop is S plus 1 equal to 0, S equal to minus 1. What is the open loop poles? Open loop poles is S plus 2, which is equal to 0, and S is equal to 0 and minus 2. So this is the closed loop poles. And this is the, this is the open loop poles, and this one is the open loop zeros. Okay, so when we plot, so you have a real axis, imaginary axis, and it will be located over here, zeros, -1, -2, and over here, poles at the origin. Okay, origin, okay. 0 is the origin. We call it as the origin. Okay, the center of the S-plane where the value is 0. So when we take a closed loop, which is K over S plus 1 and over S plus 4 over S cubic and so on. So we can see that the closed loop zeros now is S plus 1, S plus 4, which is -1 and -4. That is the open loop, closed loop zeros. But for this particular equation here, S cubic plus N plus K S square plus 8 plus 4KS plus 3K, where K is the gain, okay? So the closed loop poles is varied. The value is varied with a different value of gain K. Okay, if you K is equal to 1, so you factorize, it will become different from the other value of the closed loop poles. Okay, right. So far, any questions? Any questions?
No question.
All right, no question. Right, and then the concept to define the root locus is given by these examples, where you have two gain here, which is K1 and K2. Okay, this is K1 and is the gain, and is the gain for the control system. And from here, what is the open loop zeros? What is the value of open loop zeros? Ideal. Ideal. What is the value of the open loop zeros? Ideal. So 0 and -10. Open loop zeros is not exist. Closed loop, open loop poles is 0 and -10. Open loop poles. Okay. And open loop zeros is not exist because there is no polynomial between K2. Okay. So how the gain K affected the closed loop poles and system specifications? So first you have to find the closed loop. So this is open loop and this is the closed loop. So you let and assume K1 multiplied by K2 is equal to K. Okay, and then you find the closed loop. So you will get K over S square plus 10S plus K. So this S square plus 10S plus K equal to 0 is known as characteristic equation. Repeat after me. Characteristic equations. Guys, characteristic equations.
Characteristic equation.
So when this equation equals to 0, so it will give you the value, okay, of closed loop poles. So when you when you give the different value of k, so it will give a different closed loop poles, which is located as here, k0 minus 10, 0, k5 minus 9.47, minus 0.53, and when you increase to 30, it will give you closed loop poles in complex number until 50. So this is the data. So the data we plot into the S-plane, which is shown here. Okay, from minus 10 to 0 along the line, you have many closed loop poles, okay, the blue color, which have a different value of k. Okay, so the root locus paths from minus 10 to 0 will meet each other at minus 5, and then one will goes up and one will go down. Okay, so it will give you a different value of gain k. Okay, right. So any questions before we ended the class? Chong Jin Su. Chong Jin Su.
Yes. Yeah. Yes.
Any question, Chong?
So clear. Maybe I need to read it again.
I have one question for you, ma.
Yeah. Let me try.
What is actuating signal? Miss Chong, what is actuating signal?
Oh, input. Sorry.
What is actuating signal?
Input minus output signal. Isn't it?
Give you the actuating signal. Elisa Rosalie. Elisa.
Yeah.
Elisa, any question?
Yeah.
Any question?
No,
I have one question for you. I have one question for you. What is origin? What is origin?
Hello,
Yeah.
doctor.
What is origin?
What is origin? What is what?
Origin.
Origin. Origin.
Hmm.
Center of the graph.
Center of the S-plane. Center of the S-plane.
S-plane.
Adam.
Okay.
Adam.
Yes, brother.
Adam.
Yes. Yes, brother.
What is the difference between closed loop poles and open loop poles? What is the difference between open loop poles and closed loop poles?
Not sure, brother.
Same question go to Louis Shi. Louis Shi square. Shi.
Yes, doctor.
What is the difference between open loop poles and closed loop poles?
The closed loop poles will be affected by the gain, and the open loop will not.
It will not affected by the gain K. Okay, you understand? All right, guys. We ended our class here, and we'll continue our class inshallah on Monday. What is the date of Monday? Jingwei? Yeah, Yingwei.
Yes.
What is the date of next Monday?
The date of next Monday, 27th.
27th of March.
Yeah.
Okay, I will give you the time, the date, and the link. So meanwhile, I would like to take this opportunity for the Muslim brothers and sisters, Ramadan Karim. Selamat menyambut bulan puasa. Besok puasa. Besok puasa. Azmil, puasa tak?
Puasa.
Irfan? Irfan? Irfan tak puasa. Vicky, puasa tak?
No.
Puasa. Okay, selamat menyambut bulan puasa. Holiday mah? Tomorrow?
Holiday, doktor.
Thursday,
Balik kampung.
holiday. Friday, holiday. Saturday, holiday. Sunday, holiday. Happy holiday, 4 days. Okay? See you guys. Thank you very much.
Thank you, doktor.
Thank you very much. Sheshe
Thank you,
ni.
Doctor.
Shukran.
Thank you, doctor.
Shukran Habibi.
Thank you, doctor. Thank you, doctor.
Ya.
Puasa, doktor.
Ya.
Doktor. Selamat puasa,
Thank you, doctor.
Bye.
Thank you, doctor.
Bye.